Okay. Okay, so let's start today's class on the virtual lab experiments. So I'm going to share the screen. Yes, yes. Can you see my screen?
Yes, sir. It's visible.
Okay, fine, fine. Okay, so today's class is scheduled for the virtual lab experiments. Okay, so we have two virtual lab experiment. One is the virtual lab experiment on natural convection, and another one is on the black body radiation, that is to determine the Stephen Boltzmann constant. Okay, so we will discuss this one by one. Okay, so let's see how to perform this experiment. Okay, the template for both the experiments I have already sent. Okay,
Okay, sir.
well in advance. Okay, so let's see how to perform this experiment. So I'd shared the list of experiments with all of you. So in the list, I have also I'd mentioned the link for performing the experiment. Okay, so that
Okay, sir.
link was there. Okay,
Yes, sir.
just I will show it to you, the experiment list. This is the experiment list that I have already shared with all of you. So this is the link for assessing the virtual lab experiment. Okay, so this is the one way to perform this experiment, and another simple way to perform this experiment is on the Google. You just type Amrita University Heat and Thermodynamics. Yes, can you see my screen, Google, on your screen?
Yes, sir.
Okay. So on the Google, you just type Amrita University Heat and Thermodynamics. Okay. So okay. So now it will open this. Now you have to click on the first link, that is a Heat and Thermodynamics Virtual Lab Physical Sciences. You just click on it, so it will open a page that will display the list of virtual lab experiments on the heat and mass transfer. Okay, so you just we will click on the experiment that we want to perform. So we have to perform this heat transfer by the natural convection, and we have to perform the black body radiation, that is a determination of the Stefan's constant.
Sequence
Okay,
course.
so first of all, we'll
Okay.
perform the heat transfer by the natural convection. So we will click on it. Okay, so it will open this page. Okay, so you can see here 7 tabs are there. Tab number one is a theory tab in the that is already uh, enabled. Okay, by default theory tab will be enabled. So this in this theory tab you will get what is the main aim of this experiment, the details related to the apparatus. Okay, and the theory related to this experiment, and the concept of natural convection. Okay, now what is the mathematical expression? Okay, for calculating the heat transfer by the convection and the Nusselt number, what are the applications? So in short, we can say in the theory tab you will get all the details related to the concept of natural convection, as well as all the details related uh, uh, to the concept of natural convection, and all the details related to this experiment. Fine. Just a minute, some others are also uh, joining, so let me uh, take inside this. Just give me a minute. Okay. Okay, so let's continue. Okay, so you can see here. So we were discussing that. So 7 tabs are there here. Okay, so in the theory tab, that is by default, that is already enabled. So we can say by default it will be enabled. And in the theory tab, you will get all the details related to this experiment, and all the details related to the concept of natural convection. Now the second tab is the procedure tab. Here all the steps are available to perform this experiment. Just read each and every step and just follow it, so we can easily perform this experiment. Okay, now the tab number 3 is the self evaluation. Here you can say the MCQs are there, so we can solve you can solve these MCQs. Okay, and but it is not the part of submission. You can solve the MCQs and submit it. Okay, and you to test your knowledge, to enhance your knowledge, you can solve those MCQs. Fine. But as far as the experiment is concerned, so there is no relation with this as self-evaluation. That is the MCQs with the performance part of this experiment. Fine. Now the fourth tab, that is a simulator tab. So in this tab, when you will click on it, okay, so it will open this, and you can see the setup of this experiment. And here the sliders are there. So you just slide the slider, and we can give the input value to the different parameters. When I slide the slider on the left hand side, so I can reduce the value. When I slide the slider on the right hand side, so I can increase the value. Here a drop down list is there, so I can select the material also. Okay, and here you can see a setup is there. Okay, so I will discuss the setup and then I will come back here. Okay, and then we will perform this experiment. Okay, so the simulator tab, the most important one for making the simulation, because in the virtual lab experiment we are going to make the simulation only. Okay, now the tab number 4 is the assignment tab. When you will click on it, so it will open the different questions. Okay, so these questions or problems you can solve for enhancing your knowledge, for testing your knowledge, but it is not the part of submission. No need to solve these problems for as far as the submission part is concerned. Okay, if you want to solve and you can submit it, so it's okay. So it's well and good, but as far as the self evaluation part, this MCQs and this assignment, okay, the questions, okay, so you can solve it for testing your knowledge, for enhancing your knowledge, but it is not the part of submission. And reference, you can see when you will click on it, so you can get the information about the references that the author has referred for creating this virtual lab experiment. Okay, so that is also not very important for us. Okay, now the seventh tab, that is the feedback tab. So for the feedback tab, it will ask for the login. Okay, so remember, first of all, if you have not signed in for this virtual lab experiment, okay, you are visiting this website for the first time. So first of all, what you have to do, first of all, you have to register yourself in this website. Okay, so after successful registration, you will get one username and password. So from the next time onwards, you can visit, you can log in this virtual lab website with that particular username and password. Fine. And it will ask for login only for the two tabs, that is the simulator tab and for the feedback tab. Fine. Otherwise, it will, for rest of the tabs, it will not ask for the login. Okay, so first of all, if you have never visited this website, so you just register yourself, and after successful registration, you will get one username and password, and from the next time onwards, you can visit this website with that particular username and password. And this username and password is required for making the simulation. That means for simulator, it will ask for login, and for feedback, it will ask for login. Okay, so how can I? Okay, so I've already registered, so I can log into this username. Okay, so I've logged in to this. Okay, so it will ask for the feedback. Okay, so so what you have to do? Okay, just listen it carefully. First of all, okay, first of all, I will tell you how to complete the write-up. Fine. First of all, how many tabs are important as far as the submission part is concerned? The tab number 1, that is theory tab. The tab number 2, that is the procedure tab. Tab number 4, that is the simulator tab for making simulation. And the tab number 7, that is the feedback tab. Okay, the self-evaluation tab, assignment tab, and the reference tab is not important for us as far as the submission of this experiment is concerned. Fine. And it is mandatory for all to give the feedback. Okay. And you have to submit this experiment in a soft copy as well as in the hard copy. Okay. So I will create the activity in the LMS. So, okay. So you have to upload this virtual lab experiment in the activity created on the LMS, and you have to take the printout, and okay, so I will assess the experiments in hard copy. Okay, so the details will be there. Okay, in that I've already shared the templates. Now let's see how to complete the template. Okay, so just see, and then okay, so I've divided the discussion part in the three parts. First part is how to complete the write up of this experiment. Second one is we will understand all the concept of this experiment and how to perform this experiment. Okay, everything well in detail, and then the third part is how to make the simulation. Okay. Yeah, yes, yes. You can hear me properly now?
Yes, sir, you're audible.
Okay, fine. So let's see. So this is the template for completing this experiment. Okay, so you mention all your details here, name, roll number, everything. Okay, and now this experiment number 9. Now the virtual lab details. Now what you have to do here? Okay, for the virtual lab details. Okay, you just come here on the website. You click on the theory tab. You copy all the details. Okay, you copy all the details, the aim, apparatus, everything from the start to end up to the application part. You copy it, select it, copy it, and paste it here in the word file template. Okay, fine. Now after this, ठीक है, यहाँ का हमने theory टैब का पूरा डिटेल कॉपी पेस्ट कर लिया यहाँ पर वर्ड फाइल टेम्पलेट में, वर्चुअल लैब डिटेल में. उसके बाद हम क्या करेंगे? देन just a minute. Okay, now we will go to the procedure tab. We'll click on procedure tab. Now here also we will select all the details of the procedure tab from the start to the end, everything from the start to the end. We select it, we'll copy it, and we will paste it here. ठीक है, तो यहाँ वर्चुअल ऐप डिटेल में जहां पर हमने ये थ्योरी टैब का डिटेल जहां पर फिनिश हुआ है, वहां उसके नीचे ही हम लोग वी विल पेस्ट ऑल द डिटेल्स फ्रॉम द प्रोसीजर टैब. ठीक है, उसके बाद फिर क्या करेंगे? नाउ आफ्टर दिस वी विल गो टू, विल क्लिक ऑन द सिमुलेटर. अभी सिमुलेटर में क्या करना है देखो, यू हैव टू टेक द प्रॉपर केयर. फर्स्ट ऑफ ऑल यू जस्ट ओपन इट इन अ फुल स्क्रीन. सो यू क्लिक हियर फॉर ओपनिंग इट इन द फुल स्क्रीन. Okay, and after this you just click on show cross section so this internal structure can be visualized. Okay, so you just click on this show cross section. You just see now in this situation. Okay, you just take the okay, in the without performing the experiment, you just take the screenshot, copy that screenshot. Okay, and paste it here below this. ठीक है, जहां पर हमारा प्रोसीजर टाइप का डिटेल खत्म हुआ है वहां पर आप इसको सेटअप डायग्राम. ओके, हेडिंग डालेंगे सेटअप डायग्राम एंड यू पेस्ट दैट द स्क्रीनशॉट ऑफ इट. ओके, और याद रखिए कि ये आपको जो स्क्रीनशॉट है ऐसी सिचुएशन में ही लेना है. यू जस्ट ओपन इट द सिमुलेटर. ओके, यू ओपन इट इन द फुल स्क्रीन. Okay, and you adjust it in such a way that all the details should be readable on the, should be there on the screen and should be easily रीडेबल ऑन द स्क्रीन. अभी देखो यहाँ पर मैंने फुल स्क्रीन में से ओपन किया है, आप हमें पूरा सेटअप भी दिख रहा है, ऑल द सभी डिटेल्स भी दिख रहे हैं यहाँ पर. ठीक है, तो इस तरीके से हम उसको स्क्रीनशॉट लेकर कॉपी पेस्ट करेंगे. ठीक है, तो ये हमारा सो वी हैव कंप्लीटेड दिस पार्ट वर्चुअल लैब डिटेल्स. ओके, नाउ एनालिसिस पार्ट. अभी एनालिसिस पार्ट में फर्स्ट क्या है? फॉर सेम वोल्टेज मेक सिमुलेशन फॉर डिफरेंट मटेरियल कीपिंग इनपुट वैल्यूज एज कांस्टेंट. तो इसमें हम क्या करेंगे? यू जस्ट सी द सिमुलेटर. यहाँ पे क्या है? वोल्टेज वैल्यू विल बी सेम and we have to make the number of simulations for the different material and all the input values will also be same or constant. तो देखो इसमें क्या करना है हमें, ये देखो आप यहाँ से वोल्टेज वैल्यू आई कैन चेंज. यू जस्ट सी हियर 100 वोल्ट्स. ओके, एंड ये सपोज 110 वोल्ट ये मैंने कर दिया. राइट, तो फॉर द सेम वोल्टेज वैल्यू अब यहाँ पे देखो ड्रॉप डाउन लिस्ट देखो, यहाँ पे डिफरेंट मटेरियल्स आर देयर, एल्यूमिनियम, कॉपर, आयरन, सिल्वर, स्टील. ओके, सो हम क्या करेंगे? विल सेलेक्ट वन मटेरियल एट अ टाइम. ओके, और हम आगे कोई भी एक डायमेंशन फिक्स कर लेंगे. सपोज जैसे मैंने हाइट फिक्स कर दिया 76, डायमीटर फिक्स कर दिया 8.1, लेंथ ऑफ द सिलेंडर फिक्स कर दिया 57 सेंटीमीटर, थिकनेस मैंने फिक्स कर दिया 0.23 सेंटीमीटर. ओके, तो हम क्या करेंगे? फॉर सेम इनपुट वैल्यू, दैट मींस फॉर एवरी केस आई विल कीप माय वोल्टेज वैल्यू एज सेम एज 110 वोल्ट सपोज, है ना. I will and all these input parameters, that is width of the wooden box, height of the wooden box, diameter of cylinder, length of cylinder, thickness of cylinder, these values will also be constant. Okay, I will select only, I will just change the material. Okay, and I will click on the power on. Okay, I will click on the power on. In this way, it will start the simulation. And after the completion of the simulation, you have to take the screenshot, copy that screenshot and paste it at the required place in our Word file template. ठीक है, सेकंड टाइम में करना है तो आप इसको रीसेट पर क्लिक करेंगे और उसके बाद आप फिर से जस्ट 100, देखो यहाँ से 110 सेम वोल्टेज वैल्यू दे दिया 110, यहाँ पर बस मैंने मटेरियल चेंज किया बस। ठीक है, इसको यहाँ पर आप शो क्रॉस सेक्शन कर दो और उसके बाद ओके जस्ट सो क्रॉस सेक्शन कर दिया एंड सेम इनपुट वैल्यूज दे दो जो हमने पहले दिया था। सपोज तो 76 है ना, जो भी था 8.1 आई थिंक, सेम इनपुट वैल्यू all that means we have to give the same voltage value and all these input parameters will be same. The only thing is we are just changing the material and we have to make the simulation. And after the completion of each and every simulation, we have to take the screenshot, copy that screenshot and paste it at the required place paste it at the required place in our Word file template. ठीक है, तो यहाँ पर क्या हो जाएगा, ये फर्स्ट केस के लिए अभी देखो कितने मटेरियल हैं अपने, मटेरियल कितने हैं, 5 हैं, है ना, एल्यूमिनियम, कॉपर, आयरन, सिल्वर, स्टील। तो यहाँ पर अपने 5 स्क्रीनशॉट्स आ जाएंगे यहाँ पर फर्स्ट केस के लिए। अभी सेकंड केस के लिए क्या है, फॉर द सेम वोल्टेज वैल्यू, दैट मींस वी हैव टू कीप द वोल्टेज वैल्यू सेम, we have to make the simulation for the different material with different input values. That means here now next time, okay, you just make 5 more simulation. The only change is here we will change the input parameters also. ठीक है, तो यहाँ पर क्या है, वोल्टेज वैल्यू तो सेम रहेगा, सपोज 110 वोल्ट, और मटेरियल डेफिनेटली वी आर गोइंग टू चेंज, और मटेरियल चेंज के साथ साथ हम लोग वी विल चेंज द इनपुट पैरामीटर्स आल्सो। 5 materials are there, so we will make the 5 simulation. The only change is here in this case we are along with the changing the material, we are changing these input parameters also. Okay, अभी देखिए इसमें एक थर्ड केस भी हो सकता है. What can be the third case? The third case can be for the different voltage value, make the simulation for the different material with different input values. That means for the case number 3, we can change the voltage value also and we can make the analysis and we can compare the results. Okay, but I have not given this case 3. Okay, you just make the simulation for these 2 cases only. So 5 simulations for case 1 and 5 simulations for case 2. ओके, तो यहाँ पर केस 1 के नीचे आपके 5 सिमुलेशन आ जाएंगे, उसके स्क्रीनशॉट आ जाएंगे, और केस 2 में भी 5 सिमुलेशन और उसके स्क्रीनशॉट आ जाएगा। अभी कैलकुलेशन में आप क्या करेंगे, कैलकुलेशन में मैं आपको यू जस्ट सी दिस, अभी देखो इसके नीचे जो है ये एक्सेल शीट है। ओके, तो क्या करेंगे, जो हम यहाँ पर जो इनपुट पैरामीटर्स देंगे, जो वैल्यूज है, वही वैल्यूज हम यहाँ पर वी विल पुट द वैल्यूज हियर इन दिस टेबल। सपोज वोल्ट मेरा मेरा मटेरियल है कॉपर, तो मैं, है ना, तो इस बार मैंने सपोज 110 वोल्ट, मेरा सपोज करंट था 0.31 आ रहा, तो वो मैंने एंटर किया। ओके, अभी डायमीटर, वो जो भी वैल्यूज हैं, द इनपुट वैल्यूज जो यहाँ पर हैं, है ना, the values that I have given for making the simulation, the same values I will use here and I will feed the values here in the table. Okay, so the table is a calculator, so you just feed the input value, so it will automatically give the final results. I will show you. Okay, so from this you can see the analytical results also. Okay, तो यहाँ पर आप क्या करो, ये सिमुलेशंस के बाद यहाँ पर आप इन सिमुलेशन के नीचे ये जो टेबल है इसका भी आप स्क्रीनशॉट ले लो, या फिर आप एक टेबल ही बना लो अलग से, यहाँ पर कैलकुलेशन कर लो और यहाँ की कैलकुलेशन, यहाँ की जो भी वैल्यूज हैं फ्रॉम दिस टेबल यू जस्ट कॉपी एंड पेस्ट इट इन सम अदर टेबल। ठीक है, अगर आप यहाँ देखो कैलकुलेशन तो यहाँ से कर लो आप, बट हियर यू कैन सी द टेबल जो है फुल टेबल इज नॉट विजिबल, अदरवाइज आपको क्या करना पड़ेगा, इसका स्क्रीनशॉट लेने के 3 पार्ट्स में आप यू कैन टेक द स्क्रीनशॉट टू कवर द एंटायर टेबल। अभी देखो इतना पोर्शन दिख रहा है टेबल का, ऐसा स्क्रीनशॉट ले लो, फिर स्लाइड करके यहाँ से हाफ सेकंड पार्ट में स्क्रीनशॉट ले लो टेबल का, उसके फिर स्लाइड करके रिमेनिंग पार्ट टेबल का ले लो। तो 3 पार्ट्स में, है ना, यू जस्ट फीड द वैल्यू, ऑटोमेटिकली कैलकुलेट कर देगा। और उस टेबल को कंप्लीट करने के लिए उसको है ना 3 पार्ट्स में वो टेबल आप कवर कर सकते हो, है ना। स्क्रीनशॉट ले लो, फिर स्लाइडर को स्लाइड करो, फिर स्क्रीनशॉट ले लो, फिर थर्ड टाइम स्लाइडर को स्लाइड करो एंड यू टेक द स्क्रीनशॉट। तो यहाँ पर जो है आपका जो सिमुलेशन है उसके है ना उसके नीचे ही आप यू कैन पेस्ट द स्क्रीनशॉट ऑफ दिस टेबल। ओके, और वन मोर वे टू प्रेजेंट योर वर्क एज, क्या करो यहाँ पर, यू यूज दिस टेबल। ओके, द रिजल्ट इज जनरेटेड। उसके बाद आप क्या करो, यू क्रिएट द टेबल इन आइदर इन एक्सेल और वर्ड। Okay, and you copy all the values from this table and you paste these values in the table that you have created either in Excel or Word। और वो जो टेबल है उसको कॉपी करके आप इधर डायरेक्टली पेस्ट कर दो इधर एनालिसिस पार्ट में। इससे क्या है, आपको 3 स्क्रीनशॉट्स नहीं लेने पड़ेंगे, टेबल एक ही बार में कॉपी करके पेस्ट हो जाएगी। So we can see the analysis. Table will show the analytical result and and the screenshots will show the simulated results. Okay. Now in the calculation part, you have to show one sample calculation. Okay, how we are here in this, as far as this experiment is concerned. So we have to find the convective heat transfer coefficient, that is H, and the Nusselt number. Okay, so how we are calculating this H, convective heat transfer coefficient, and how we are calculating Nusselt number. Okay, so Q is equal to HA delta T. So from this Q we can, so from this Q is equal to HA delta T, that is Newton's law of cooling. We are determining this H. Okay, and Nusselt number is equal to HL by K. So from this we can find the Nusselt number. Okay, so we have to show you have to show just one sample calculation. Okay, here you either type it or you make the calculation manually in the notebook, and uh, you just take the picture of that, copy that screenshot and paste it here for the calculation part. Okay, और result क्या आ जाएगा आपका, result आ जाएगा the calculated value of convective heat transfer coefficient है ना, simulated value is equal to this result आप ऐसा लिखो, convective heat transfer coefficient simulated, okay, by the simulation is equal to this, Nusselt number value by the simulation is equal to this, convective heat transfer coefficient analytical is equal to this, and the Nusselt number analytical is equal to this. So you can write the result. And what is the conclusion? We have uh, performed the experiment on the natural convection and performed the experiment for the 2 cases. Okay, and for perform the experiment for the 2 cases. Okay, that is for the this one, for the same voltage value, different material keeping input values as constant. And for the second case, for same voltage value, we are making simulation with the different material with different input values, and got the values in standard range, and the simulated result and the analytical results are comparable. So that can be your result. Okay, or so sorry, conclusion. Okay, so what can be the conclusion? We have performed the experiment on, or in short, you can write the concluding remark in brief. We have performed the experiment on the natural convection and determined the uh, convective heat transfer coefficient value and the Nusselt number with the help of simulation and analytically, and we got the comparable result. Fine. That means, okay, we have determined the convective heat transfer coefficient and Nusselt number for this natural convection heat transfer coefficient with the help of simulation and analytically. And the analytical results are comparable with the simulated result. So that can be your conclusion. Fine. Now let's see. Now let's. Okay, so I have told you how to complete the write-up. Yes, understood.
Yes, sir.
Okay, now let's understand. Okay, let's discuss the experiment. Okay, so let's see the theory part. Okay, so here, what is the main aim for performing this experiment? The main aim for performing this experiment is to determine Okay, it is wrong. Okay, here it is mentioned as overall heat transfer coefficient. It is not overall heat transfer coefficient. Overall heat transfer coefficient is U. Okay, we have to calculate convective heat transfer coefficient, that is small h. Okay, so you make correction. Our main aim is to determine the convective heat transfer coefficient at the surface of a given vertical metal cylinder by the natural convection method. Okay, that means we have to determine the convective heat transfer coefficient for a vertical metal rod or okay, and rod is like a cylinder. You can see here. This is a rod. है ना? So rod is like a cylinder. Okay, so we can say we have to determine the convective heat transfer coefficient at the surface of a vertical metallic cylinder or rod by the natural convection heat transfer method. And second aim is to determine the Nusselt number. That means we have to determine small h, that is convective heat transfer coefficient, and the Nusselt number. So we will find these values by making simulation. That means we will find the simulated values of both these parameter, that is convective heat transfer coefficient and Nusselt number. And after this, we will find this convective heat transfer coefficient and Nusselt number analytically, and then we will compare our analytical result with the simulated result. So that is the task. Now let's talk about the apparatus. You can see what, okay, so here, what is this? This is a duct. You can see this is a duct, and inside, okay, so this is a duct. This duct is open at the bottom and at the top. Okay, so and what we have done, the material of this, you can say, this duct is the wooden. Okay, this is a wooden rectangular duct. That means the material of this duct is wood. So, okay, so what we have done? Okay, so here we have taken a rectangular duct, and the material of the duct is wood, and this duct is open at the bottom and at the top. Okay, here inside this duct we have placed a metallic rod or metallic cylinder in a vertical fashion. Okay, and here you can see we have placed 6 thermocouple, one at the bottom of this enclosure or duct, and that is okay, and another one at the top of this duct or enclosure, and we have placed 4 thermocouple, that is T2, T3, T4, T5 at the 4 different location along the length of this vertical rod or cylinder. Okay, we have placed the heater along the length of this vertical cylinder or rod. Okay, okay, so ultimately we have placed 6 thermocouple, one at the bottom of this duct, another one at that. Okay, so it will record the temperature T1, another one at the top of this duct, that is T6, so we can record the temperature at that location, and 4 thermocouple, T2, T3, T4, T5 at the 4 different location along the length of the vertical cylinder or rod. And we have placed the heater along the length of this vertical cylinder or rod, and the airflow takes place inside this rectangular duct or enclosure, okay, from the bottom to the top, but this airflow takes place naturally or freely. Okay, we are not using any external agency for this airflow. That's why it is natural convection heat transfer. So what happens, this heater will heat the surface. Okay, we'll provide the power supply to the apparatus, we will on the heater. The heater will heat the surface of this um, um, uh, vertical metallic cylinder or rod, and airflow takes place freely inside this rectangular duct. So heat transfer takes place from the surface of this vertical rod or cylinder to the air that is flowing inside the duct freely. So we can say the heat transfer takes place by the natural convection. Fine. So you can say this, है ना? The wooden, hollow wooden rectangular tube. This is the heater that is placed inside the cylinder. This is the hollow metallic cylinder, and these are the thermocouple. So overall, we have used 6 thermocouple at the 6 different locations. One at the bottom of the duct, another one at the top of the duct, and 4 thermocouple we have placed at the 4 different locations along the length of this vertical metallic cylinder or rod. Okay, now the theory. So basically, what happens? We know when the heat transfer takes place by the natural convection. Okay, so we know the mechanism of the natural convection very well. Basically, when the natural convection heat transfer takes place, so we apply the Newton's law of cooling for determining the value of H. Okay, because according to the Newton's law of cooling, Q is equal to HA delta T. Okay, so from this we can find the value of H, that is convective heat transfer coefficient. But so we can calculate this H, but some additional information is also required to understand the mechanism of this convection. So other factors are also there, that is the shape, dimension, orientation, and of course the temperature difference between the surface of the body and the surrounding fluid. So these factors are expressed in terms of the dimensionless numbers. That's why the study and the analysis and the analysis of these dimensionless numbers becomes very very important in order to understand the natural convection heat transfer phenomena. Also, different dimensionless numbers are there that we have already discussed well in detail during lecture. What are those dimensionless numbers which are important for making the analysis of convection? Reynolds number, Nusselt number, Prandtl's number, Grashof number, Stanton number, okay, Froude's number, Peclet number, and so on. Okay, so Reynolds number is the most important number for making the analysis for the forced convection, and Grashof number is the most important number for making the analysis for the free or the natural convection. Okay, so let's see how to calculate this Q. So we can say this Q is equal to Ka dt by L. So what is this? This is the suppose if a solid is there. Okay, so suppose a plain wall is there and heat transfer takes place through the thickness of the wall. So definitely heat transfer takes by the conduction. So how can we calculate the heat transfer by the conduction? By applying Fourier's law of heat conduction. So Q is equal to minus Ka dt by dx. Dx is the thickness. So here in place of thickness we have taken L thickness. Okay, but here our case is the for the okay. So in that case also, what is T? So we have not considered. We are making the analysis for the steady state. So ignore this T. Okay, here the experiment is based on convective heat transfer coefficient. So this expression is applicable for us. If the heat transfer takes place with the convection, so we'll apply the Newton's law of cooling. So according to Newton's law of cooling, Q is equal to HA delta T, where H is the convective heat transfer coefficient, A is the surface area, delta T is difference between the surface of the body and the surrounding fluid. That means difference between the temperature on the surface of this vertical metallic rod and the air that is flowing inside the vertical duct. Oh, sorry, rectangular duct. Okay, so Ts minus T, that is uh, difference in the temperature between the surface temperature on this vertical metallic cylinder and the air that is flowing inside this rectangular duct. Suppose Ta is the temperature of the air that is flowing inside the duct, and Ts is the steady state temperature on the surface of this vertical rod or cylinder. Okay, so Ts minus Ta will be delta T. Okay, so we know the unit of H, this is watt per meter square per Kelvin. Okay, delta temperature difference between the surface of the object and the surrounding fluid, right? So in this way we can find. Now the Nusselt number, okay, all these the dimensionless number with the physical significance of all the dimensionless numbers with mathematical expression, that is where that we have already discussed well in detail during lecture. Okay, so we know the formula for calculating, we know the definition of the Nusselt number, what is the significance of Nusselt number, and what is the mathematical expression for calculating Nusselt number. So Nusselt number is equal to HL by K, where H is the convective transfer coefficient, L is the length, and K is the thermal conductivity. Okay, K is the thermal conductivity of the fluid. Okay, here the air is flowing inside the rectangular duct, so we have to take the thermal conductivity of the air, and L is the characteristic dimension. Okay, so that can be either length or diameter. Okay, so here our okay, L will be the characteristic length. Okay, so n is a dimensionless number or non-dimensional number, so it is dimensionless quantity. Okay, Now application, we can say it is natural convection. So we can see the application of natural convection in many areas like cooling of the commercial high voltage electrical power transformer, heating of houses by the electrical, okay, baseboard heaters, and okay, heat loss from the steam pipelines in the power plant, and maybe heat gain in the refrigerant pipelines in air conditioning appliances, and so on. Okay, so number of applications are there. The procedure tab is there. Okay, first of all, we have to choose the material. Okay, we have to choose we have to select the, we have to give the input value to the side of the wooden box, height of the wooden box, diameter of the cylinder, length of the cylinder, thickness of the cylinder. Then with the help of the white knob, we can change the voltage value. Okay, I will show you. Okay, you can see this is a white knob. I will click on this. The right arrow will increase the voltage value, and when I will click on the left arrows, it will decrease the voltage value. So I can adjust my voltage value. Okay, and will note. So we can see the voltage value with the help of this voltmeter, and will note down the corresponding current value with the help of ammeter. Will take the product of the voltage and current, and this way we can calculate the heat input value. Okay. Now power on, when you will click on the power on, so we can start the experiment. This is the power on. This is the power on. When you click on power on, so we can start the simulation. Okay, just enable this so you can see the internal structure of the setup. After completion of the simulation, the result will be generated on the bottom right corner. So we can see the result for the convective heat transfer coefficient and Nusselt number. Okay, and we have to open it in the full screen, and we have to adjust in such a way that all the details should be okay, visible in your screen. You open it in the full screen and you adjust the screen like this. Now my setup diagram is completely visible on the screen. All the input values are completely visible on the screen, and all the results are also visible on the screen. If you don't adjust the screen, then the screenshot okay, will be meaningless. Okay, so you open, first of all, you open this okay, in the you open this in a full screen, and then you adjust it properly so that all the details must be visible on the screen like this. And now you take the hand, and so in this situation, after the completion of each and every simulation, you have to take the screenshot, copy that screenshot, and paste it at the required place in our word file template. Clear? So we were talking about this. Okay, so like this, so temperature indicator, with the help of temperature indicator, we can note down the temperature value at a 6 different location from T1 to T6. Okay, so this temperature indicator will display the temperature value. We just rotate the changeover switch, the particular location will automatically display the temperature value at that location. You can see here. Okay, this is the temperature indicator. Okay, so it will display the value of T1 is equal to this, T2 is equal to this, and so on. When you will click on this arrow, so okay, so it will go to T1, T2, T3 in the increasing order. When you will click on this arrow, so it will move in the decreasing order. Okay, this is okay, so fine. So this is uh, what about this? This is a voltmeter for recording the voltage value. This is the ammeter for recording the current value. This is a white knob for adjusting the voltage value. This is the power on switch, power on off switch. This is the, you can say, okay, this is the system. Rectangular duct open at bottom and top, and this is the arrangement of the vertical metallic cylinder and the arrangement of thermocouples, and the heater is provided for the length of this hollow rod or cylinder, and this is already discussed. The temperature indicator, which will okay, just click on the arrow, so it will display the temperature value from T1 to T6. You can read the temperature value with the help of the temperature indicator. And what is this? This is a stopwatch. It will display the time for attaining the steady state. So this is all about the setup. Now let's come to here. Okay, so that's it. So just we'll follow it. And then what about this? This is the table for making the calculation. Okay, so metal rod here, change the different material, aluminum, copper, and so on, the voltage value, the current value, and T1 T6 value, that is the temperature value at the bottom and at the top of this rectangular duct, and T2 to T5 value, that means the temperature value at the four different locations along the length of this vertical metallic cylinder. Okay, so ignore this time factor because we are making the analysis for the steady state, and we have the voltage value, we have the current value. We'll take the product of voltage and current. In this way we can calculate heat input value in watt. What is this area? Okay, area of what? Area of the cylinder or the rod. Okay, fine. So we know okay, rod is like a cylinder, so cylinder is having area pi dl. We have the diameter of this cylinder, okay, rod, or and we have the length of this rod. Okay, we know the value of the diameter of this rod, and we know the length of this rod. Okay, and the rod is like a cylinder, so we'll use the formula for calculating the surface area of the cylinder, that is pi dl. We can calculate it in meter square. Now delta t, what is this delta t? This is the average steady state temperature on the surface of this vertical metallic cylinder minus average steady state temperature uh, inside this duct. Okay, fine. So delta T is what? Average steady state temperature on the surface of this vertical metallic cylinder minus average steady state temperature of the air inside this rectangular duct or enclosure. So ultimately, the heater is heating the vertical rod or cylinder, and the air is freely flowing inside the rectangular duct. So heater, okay, so heater will heat the surface um, uh, of this vertical metallic cylinder, and air is freely flowing inside this rectangular duct. So heat transfer takes place by the natural convection. Okay, the air that is flowing inside the rectangular duct. Okay, so that is freely flowing. Okay, the air is flowing naturally or freely. We are not using any external agency. That's why it is natural convection heat transfer. Okay, so heat input is the product of voltage and current. So we have calculated this Q value. Now we'll apply the Newton's law of cooling for calculating H. So Q is equal to HA delta T. So so Q is equal to VI. Okay, Q is equal to V into I. So we have calculated Q. Now a surface area we have already calculated, delta T value we have already calculated. In this way we can calculate convective heat transfer coefficient. Okay, so the unit of convective heat transfer coefficient is watt per meter square per Kelvin. Okay, Nusselt number is equal to HL by K. We will put the value, we will put this calculated value of H here. L value, the L value we know. Okay, the characteristic length is the length of this. Okay, length of this cylinder or the vertical rod. We put here, and K is what? K is the thermal conductivity of the air. Okay, so ideally you should first of all you should calculate the mean film temperature, and at mean film temperature from the property of saturated air table you should take the thermal conductivity of this air. But no need to do this exercise here. We have already mentioned the thermal conductivity of for the air is equal to 0.024 watt per meter per Kelvin. This value you use for making calculation. Okay, however, this is not the accurate way to calculate the dimensionless number. The accurate way is, first of all, we have to calculate the mean film temperature. And what is mean film temperature? It is the average. Mean film temperature is Ts plus Ta divided by 2. That is, it is the average of the surface temperature and the ambient temperature. So we'll calculate mean film temperature, and at mean film temperature from the properties of saturated air table, we will note down the different thermophysical property. Okay, so we can say, and thermal conductivity is one of the most important thermophysical properties. We'll note down that value. Okay, and here we, in the result we will put the heat transfer coefficient value, calculated heat transfer coefficient value, and the calculated Nusselt number value. Clear? Now let's make the simulation. Okay, so we'll go to the simulator. Okay, so let's make the simulation. Okay, just give me a minute. Okay, so let's make the simulation. So here you just see here a drop down list is there. Okay, so uh, so case number one is we have to, for the same voltage value, okay, for the different material, keeping the input value same, we will make the simulations. Case number one. Okay, and for case number two, we along with changing the material value, we will change the input parameters also. That means we'll change the dimensions also. Now here, okay, you will click on this. Uh, so first of all, we'll select from the drop down list. We can select the material. Suppose I want to make the analysis for copper. Okay, copper किया मैंने. Okay, so first of all, you click here, show cross section, so the internal structure can be visualized. Okay, now here white knob is there. You just click here on this arrow, so we can see. We can increase the voltage value. Okay, so it is 100 volt. Okay, so I will. I have already clicked on it, so it will increase the voltage value. Suppose I'm performing for 110 volt. Okay, so it is 110 volt, right? Now we will adjust the input values, that is the width of this wooden board. Suppose I am providing 8.8 centimeter. Height of the wooden box, suppose 77 centimeter. Diameter is suppose okay, the diameter is 8.2, suppose. Length is 58 centimeter. Thickness is suppose 0.24 centimeter. Okay, now we will click on power on. Okay, so it will start the simulation. Fine, and the temperature will be displayed here, and it will keep on changing. So we have to keep watch on the temperature value. If it is changing, that means it is okay, so that means the unsteady state heat transfer takes place. Okay, and since the steady state is the limiting condition for unsteady state heat transfer, so we have to keep watch on the temperature. And okay, so if the temperature is changing, that means we have to wait. Okay, and when the temperature stops changing, that means we have achieved the steady state. So we have to stop the simulation, and then that means our simulation is over. Okay, so let's see. We will click on power on. You just see here the airflow. You can see from the bottom to the top. You can see here the time changing and the temperature also changing. Temperature change we can observe with the help of the temperature indicator, and time value we can see with the help of this stopwatch. You just see temperature changing. Okay, now the temperature stops changing. Okay, it is now it is 30. Okay, stop changing. So we have achieved the steady state, right? So just see this. Okay, so see this. We'll click on the. We will see the results. So you just see here. The result is the simulated value of convective heat transfer coefficient is 2.46 watt per meter square per Kelvin. Okay, here the unit is wrong. Okay, the unit of H is watt per meter square per Kelvin. So you just make correction. Okay, so simulated value of convective heat transfer coefficient is 2.46 watt per meter square per Kelvin, and the simulated value of Nusselt number is 79.14. Okay, fine. Now let's see. Now we will. So these are the simulated result. Now we'll make the analytical analysis. So how can I make the analytical analysis? A table is there below this. So we have done the analysis for the copper. Okay. So let's see for the copper. The voltage value was 110 volts. So let's see कितना था. You just see voltage value 110 है और current value 0.31 एम्पियर है. तो हम आएंगे यहाँ पर. We'll put the voltage value as 110 volt, and the current value is 0.31 ampere. Now the diameter of the cylinder was 8.2 centimeter ना. 8.2 centimeter लिया था ना हमने. Diameter of the cylinder, it is 8.2 centimeter, and length is 58 centimeter. Okay, so diameter is 8.2. Okay, now length 58 सेंटीमीटर था. ओके अभी हमने पुट किया. नाउ इट विल ऑटोमेटिकली कैलकुलेट द सरफेस एरिया. सरफेस एरिया फॉर ओके द फॉर्मूला फॉर कैलकुलेटिंग सरफेस एरिया इज पाई डी एल. okay, so it will automatically calculate the surface area. Fine. Now we have to put all the values. These are the temperature on the surface of this vertical metallic cylinder. Okay, so we'll put all the values of temperature. So let's go. Okay, so you just see here, you just click here on this okay arrow. So it will proceed in the increasing order and we can note down the temperature value. You see T2 is 43.61. Okay, so we'll note down this 43.61 here. 43.61. now T3 वैल्यू यहाँ पे क्लिक करेंगे. देखो 45.61. तो यहाँ पर हम 45.61 पुट करेंगे. 45.61. now T4. so you click here. so is the T4 value. T4 value is 49.61. 49.61. T4 वैल्यू सॉरी T5 वैल्यू. T2 T3 T4 हो गया. अभी T5 का वैल्यू लेंगे. T5 is this 51.61. 51.61. okay, now it will automatically calculate the average or the mean temperature on the surface of this vertical metallic cylinder. Okay, we have to feed the value in the table. It will automatically calculate the mean or the average value of the temperature on the surface of this vertical metallic cylinder. now here we have to put T1 and T6, the temperature of the air. Just see this. Click here. So this is T6. T6 is 36. We'll put the value here 36. Now only T1 is left. So we'll click here on the left arrow. So this T. Okay, so we'll come back to T1. So T1 is 30. So we'll put here 30 degrees Celsius. So you just see here. Average value of temperature on the air is average of 30 and 36, 33. Now it will automatically display the analytical result for the convectivity transfer coefficient Nusselt number. Okay, so analytical value of the convectivity transfer coefficient is 15.62 and the Nusselt number is 377.7. okay, so you can observe the result. okay, the simulated result for the convectivity transfer coefficient is 2.46 watt per meter square per Kelvin. And here the analytical value of convectivity transfer coefficient is 15.62 watt per meter square per Kelvin. However, the difference is there in the result, but both the results are acceptable because the convectivity transfer coefficient value is lying in the standard range. Because as we know, the convectivity transfer coefficient value for the gases for the natural convection lies in the range 2 to 25 watt per meter square per Kelvin. Okay, so both the values are lying in the range. Okay, that's why it is acceptable. And the simulated result for the Nusselt number was 79.14. And here the analytical value of the Nusselt number is 377.7. Okay, however, there is difference in the result. Okay, there is the big difference between the result, but both the results are acceptable. Okay, so that Nusselt number value is also acceptable for both the case, as it is coming in the range. However, there is difference between the values between the simulated result and the analytical result, but both the results we are getting in the standard range, so the results are acceptable. Okay. So likewise, what okay, now you just see here. Now the simulation is over. So okay, so we have to open it in full screen. Now you adjust it properly like this. अभी देखो इस तरीके से. अभी देखो now my the setup diagram is visible here, and now all the input parameters are also visible on the right hand side. and this option show cross section is enabled, so I can see the visualize the internal structure, and here the result is also available on the bottom right corner. You can see the result for the convectivity transfer coefficient, Nusselt number. Okay, so we have opened it in the full screen and all the details are available on the screen. Now in this situation, after the completion of the simulation, we have to take the screenshot, copy that screenshot and paste it at the required place in our Word file template. Fine. So in the now, okay, now let's make the another simulation. So we'll click on reset. Okay, now let's make the analysis for, okay, now we'll select the another material. Okay, so first of all we'll select the another material. Okay, so first of all we had done the analysis for copper. Okay, now let's select the aluminum only for this case. Now you just select here, change the voltage value. Now okay, so same voltage value we have to give, so we have given 110 volt. Now the same input values we have to give. So wooden, the width of wooden box I had given as 8.8 centimeter. Okay, same value I had given. The height I had given as 77 centimeter. Okay, diameter of cylinder I had given 8.2 centimeter. Okay, the length of the cylinder is 58 centimeter. The thickness given as 0.24 centimeters. So same input value we have given. Now we'll click on power on. So it will start the simulation. So first of all, you just click on show cross section. So internal structure we can visualize. And in fact, if we change the material also, so it changes. Okay, so physical, okay, so physical appearance also changes. Okay, now you just click on power on, so it will start the simulation. Okay, you just see the airflow takes place from the bottom to the top inside this vertical duct, but the airflow takes place freely. You can see the change in the stopwatch, and you just see the temperature continuously changing. Okay, so we have not achieved steady state. Okay, so we have to keep watch on the temperature value. Okay, now the temperature stops changing. Okay, now we have achieved a steady state. Okay, now the simulation is over. Fine. Now you just scroll it down. You can see the result. Okay, so you just see the result. This result is 2.46 watt per meter square per Kelvin, and the Nusselt number is 79.06. Okay, so we are getting the same simulated result as we got for the copper as the material. Okay, so now the simulation is over. Now in this situation, okay, we have opened it in the full screen, and we have adjusted our screen in such a way that all the details are available on the screen. Here you can see the setup diagram is uh, available. You can visualize it completely, and all the input parameters are also visible on the right hand side, and the result we can see on the bottom right corner. So all the details are available on the screen. In this stage, we will take the screenshot, copy that screenshot, and paste it at the required place in our Word file template. Okay. Now for the same values, okay, we can make the analytical result and analytical also. You just see here. Now in this case, I will make the analysis for the aluminum. So let's do this. Aluminum 110 volt, and the current reading, let's see current reading कितना है, 0.31 है. तो हमने 0.31 यहाँ पर एंटर किया. Now diameter कितना है, सेम वैल्यूज ही है. All the parameters are same. Just the only thing is we have changed the material. So 8.2, यहाँ पर 58. तो एरिया इट विल ऑटोमेटिकली कैलकुलेट. ओके, अभी टेम्परेचर वैल्यू हम देखते हैं. तो T2 43.61, सेम वैल्यू आया. ओके, नाउ T3 45.61, 45.61.
T5 4 49.61. T5 51.61. Okay, so all the temperature values, no, same temperature values we are getting. No change so far. Now it will automatically calculate mean value of temperature on the surface of this vertical metric cylinder. Now T6 is 36. Okay. Now let's see. Let's check the value of T1. T1 is 30. Okay, say exactly same value. Okay, now the average value of the temperature of air is 33 degrees Celsius. All the temperature values we are getting same. So definitely we'll get the same result. So in this case also we are getting the convectivity transfer coefficient value as 15.62 watt per meter square per Kelvin and Nusselt number as 377.7. Okay, so likewise you can make the simulation for the remaining materials. Okay, so if I have to make this next simulation, I will click on reset. Okay, so in the similar fashion, we can make the analysis for the remaining material like that is iron, silver, and steel, keeping the voltage value and all the input parameters as same. So we will observe that we will get the same simulated result for the convectivity transfer coefficient Nusselt number for all the 5 cases. And if or as far as the analytical result is concerned, we will get the analytical result for the H and Nusselt number uh, for all the 5 cases same. Fine. So we'll get the same analytical result for convectivity transfer coefficient and Nusselt number for the analytical analysis. Okay, that means if we change the material, it will not affect the convectivity transfer coefficient and Nusselt number. So there will be no change of material on the convectivity transfer coefficient and the Nusselt number. Okay, so here you can make the 5 simulation. You after the completion of each and every simulation, you just take the screenshot, copy it to the screenshot, and paste it at the required place in our Word file template. And in the similar fashion, you just make the analysis for the case 2. Case 2 is what? For the same voltage value, make simulation for different material with different input value. ठीक है, तो इसमें क्या करना है अपने को इसमें क्या करना रहेगा? सेकंड केस के लिए विल चेंज द मटेरियल. सपोज मैंने सब मटेरियल ले लिया है ना, हर बार मटेरियल चेंज करूंगा, इनपुट वैल्यू तो सेम रहेगा, वोल्टेज वैल्यू सेम. I will change the material and at the same time I will change the input parameters also randomly. Okay, so I for the same input value we'll change the material and we'll change all the input values, and we'll click on the power on and we'll make the simulation. You see the temperature keeps on changing, and as the time changes, time value we can observe with the help of a stopwatch, and the temperature value we can observe with the help of temperature indicator. Okay, now we have achieved the steady state. Okay, and so we can observe, you can make the simulation for this. Okay, so case 2 ke liye we can do and all, and in similar fashion you make the analytical analysis for the 5 cases for the case 2. Clear? In this way we can complete this, you can complete the write up of this natural convection heat transfer virtual lab experiment. Is it okay? Yes, yes.
Yes, sir.
Okay, fine. Is there any doubt or understood?
No, sir. Yes, sir. Yes, sir.
Okay, understood na?
Yes, sir.
Okay, fine. Okay, now let's discuss the second experiment. Okay, that is the Stephen Boltzmann constant. Okay, again, okay, I will show how can we perform this experiment. Just a minute. Okay, okay, in the Google you type Amrita University Heat and Thermodynamics. You click the first link, this one, physical sciences. That will display the list of virtual lab experiment that we can perform for heat and mass transfer. Now we'll click on this black body radiation determination of Stephen's constant. We'll click on it. Again, now it will not take no, now you are familiar with the virtual lab experiment. You know how to complete the write up of this of this experiment, because the rest of the procedure is same for the completion of the write up. Okay, the only thing is that the concept is same. The concept is different, and we will understand the concept and we'll perform this experiment. Okay, but as far as the completion part is concerned, so that is same, and you are already familiar with this. Okay, that I've already discussed well in detail as far as the completion of this experiment is concerned. Okay, here you can see again the same thing is there. 7 tabs are there. Theory tab. Okay, so here also the only the theory tab, the theory tab is that will be enabled by default. Okay, so here in the theory tab, we will get all the information related to this experiment and all the information related to the concept related to this experiment. That is the aim, the details of apparatus, and what is the working principle. Okay, how it is, what is the working principle of this setup or arrangement. This is the schematic of this arrangement for this experiment, and then the mathematical expression, and then finally the derivation of the Stephen Boltzmann constant that we have to determine, and the application. Okay. Now in the procedure tab, the steps are available. Just read the steps and we have to just follow it so we can easily perform this experiment. Okay, the procedure for perform this experiment. In the self-evaluation tab, we'll get MCQs. You can solve those MCQs for testing your knowledge, for enhancing your knowledge, but it is not the part of submission. Then we will click on the simulator. So just click on the simulator. So okay, so you can make the simulation, the most important one. Okay, and then when you will click on the assignment part, so it will display the question. So these assignment question you can solve for testing your knowledge, for enhancing your knowledge, but it is not the part of submission. And the reference tab, when you will click on it, so here you can get the details which the author has referred to prepare this virtual lab experiment. And then the last tab, that is the feedback tab. Okay, when you will click on it, so you can give the feedback. Yes, one more thing. Okay, so for you have to, after the completion of this experiment, you have to submit the feedback also. Okay, so you have to submit both the virtual lab experiment in soft copy on the LMS. I will create the activity on the LMS, so you have to upload the soft copy on LMS, and you have to submit both the virtual lab experiments in hard copy for the assessment. Okay, so remember, after the completion of this experiment, you have to submit the feedback for both the experiment, and you have to attach the feedback page also in your write up, both in the soft and hard copy. Fine. Now let's go ahead. So as far as the tab is concerned, so only 4 tabs are important for us. The theory tab, tab number 1, theory tab. All the details are available here in this tab. Procedure tab for performance experiments. Okay, the second tab, procedure tab, and the fourth tab, that is simulator tab for making the simulation, and the last tab, that is the 7th tab for submitting the feedback. Okay, so that is important. Now let's see how to complete the write up. You just see this is a template. I've already shared it with all of you to complete the write-up of this experiment. Now virtual lab details, calculation, result and conclusion. So what you will do? Again, in the similar fashion, you just go here in the theory tab, you copy all the details right from the start, that is from the aim, to the last, that is from the application. You just select it, copy it, and paste it here, and paste it here in the virtual lab detail. Okay, now after this, you click on procedure tab, and now in the procedure tab also you also again select all the details from the start of this tab to the end of this tab. You select it, copy it, and paste it here. Okay, below the theory tab details. Okay, theory tab detail हमने copy paste कर लिया, उसके नीचे हम procedure tab के details अभी copy paste करेंगे. ठीक है, उसके बाद आपका क्या आएगा? फिर उसके बाद हम सिमुलेटर से है ना सिमुलेशन करेंगे. सिमुलेशन
सिमुलेशन करेंगे और सिमुलेशन करने के बाद सिमुलेशन 3 केसेस के लिए करेंगे। तो यहाँ पर अपने को सिमुलेटेड वैल्यूज मिलेंगे। ये वैल्यूज वी विल पुट हियर इन द टेबल, so it will automatically give the analytical results. Okay, so after the completion of each and every simulation, you have to open it in a full screen and adjust it properly so that all the details should be uh, available on the screen. And in that stage, you just take the screenshot, copy that screenshot and paste it at the right place in our word file template. और यहाँ पर आप टेबल में भी एनालिटिकल वैल्यू के लिए टेबल जो है उसको भी यहाँ स्क्रीनशॉट ऐसे लेना है। पहले ऐसा स्क्रीनशॉट ले लो, उसके बाद इसको स्क्रॉल करके सेकंड स्क्रीनशॉट ले लो, इससे आपका टेबल 2 बार में आ जाएगा। अदरवाइज यू क्रिएट द टेबल इन द वर्ड और एक्सेल, और यहाँ पर आप वैल्यूज पुट करके यहाँ से यू पुट ऑल द वैल्यूज इन दिस टेबल, यू विल जनरेट द रिजल्ट एंड copy all the values from this table and paste it here in the table that you have created in the Excel or Word. Okay, and copy that table in the Word file template. Okay, तो इस तरीके से no need to take the multiple screenshots for this analytical analysis. Okay, so three things, three trials are there, so we have to make the 3 simulations for these 3 trials. Okay, so fine, so here you just check this. तो फॉर द वर्चुअल लैब डिटेल्स, ओके, सो पहले हमारा थ्योरी टाइप का डिटेल आ गया फ्रॉम स्टार्ट टू एंड, वो कॉपी करके पेस्ट करना है इधर। और उसके बाद हमारा प्रोसीजर टाइप का डिटेल्स फ्रॉम द स्टार्ट टू एंड, यू हैव टू कॉपी इट एंड पेस्ट इट हियर। एंड देन उसके बाद यू हैव टू मेक द 3 सिमुलेशंस फॉर दिस स्टीफन बोल्ट्जमैन कांस्टेंट experiment. Okay, so 3 trials are there, so we have to make 3 simulations, and after the completion of each and every simulation you have to take the screenshot, copy that screenshot and paste it here. So 3 simulations हो जाएंगे यहाँ पे, ठीक है। और उसके बाद आपको सैंपल कैलकुलेशन दिखाना है यहाँ पर, so at least show at least 1 sample calculation here. तो वो कैसे कैलकुलेट करेंगे, either you type it here or you make the manual calculation in your notebook and you take the picture of that calculation and copy, okay, you take the screenshot or take the picture of that manual work that you have done in your notebook for making calculation, to copy it and paste it here. This way you can make the calculation. So for calculation you have to show at least 1 or 2 sample calculation. Okay, now the result will be the average simulated Stephen Boltzmann constant value. Okay, and the okay, so that you can write the average simulated Stephen Boltzmann constant value is equal to this, and the conclusion is what? Now we will compare our simulated value of Stephen Boltzmann constant with the standard value of Stephen Boltzmann constant. And we know what is the standard value of Stephen Boltzmann constant. It is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, so we will compare our your simulated value of Stephen Boltzmann constant with the standard value of Stephen Boltzmann constant. So our simulated value should be very close to the standard value of Stephen Boltzmann constant. So both the values should be approximately equal. Okay, the simulated value of Stephen Boltzmann constant and the standard value of Stephen Boltzmann constant should be almost same. So you can write the calculated value, the simulated value of Stephen Boltzmann constant is this, and the standard value of Stephen Boltzmann constant is this. So we got almost same results. So we got almost same simulated result. Okay, or you can write we got our simulated result is almost same as the standard value of the Stephen Boltzmann constant. So that can be the conclusion. And after the conclusion, you take this one, you just fill the feedback form. After the completion of feedback form, you take the screenshot, copy that screenshot and paste it here at the bottom. Okay, and paste it here at the bottom after the conclusion. Okay, so in this way you can complete the feedback, and you have to show that you have given the feedback. In this way you can complete the write-up. The soft copy of the write-up you have to upload in the LMS. I will create the activity in the LMS for the submission of this virtual lab experiment, and you take the printout of it. And for the assessment, you have to submit both the virtual lab experiment in the hard copy. Okay, so in both the soft and hard copy, the feedback should be there. Okay, if you if the screenshot of the feedback is there, then only it will be assessed. Okay, because it is compulsory to give the feedback. Fine. Now let's understand this experiment. Okay, now we have discussed how to complete the write-up of this. Now we will understand this experiment. Okay, the theory behind this, the concept behind this, and then we'll make the simulation. Okay, the second part is the understanding of the setup and understanding of this experiment and the concept and the principle. And the third and the last part is we will complete the simulation part, and then we will be able to complete this write-up of this experiment. Now let's see. So what is the aim for performing this experiment? The aim for performing this experiment is to determine the Stefan Boltzmann constant. Okay, so we will make the simulation. So after the completion of this simulation, so we will be able to find the simulated value of Stefan Boltzmann constant. So with this we will do for the 3 trials, and we will use the average value. So the average simulated value of Stefan Boltzmann constant, that will determine, and will compare it with the standard value of Stefan Boltzmann constant. Okay, now let's see the apparatus. So the apparatus is there. So basically a box is there that contains the metallic hemisphere. Okay, and we have made the provision that the annular space is there. So we will allow the hot water to flow through the annular space of this hemisphere. Okay, uh, fine. And we have to note down the temperature of at the surface of this hemisphere. That's why we have provided 3 thermocouple at a 3 different location on the surface of this hemisphere. Okay, so temperature indicator is there, so that will indicate the temperature at the different location. The heater is there that will heat the water. Suitable black body is there that we can connect at the bottom of this metallic sphere in order to close it. Okay, so what is the apparatus? So basically a box is there. Inside a box, a metallic hemisphere is there. Okay, we will take the water. We will, with the help of the water, we will heat the water, and we will allow the hot water to pass through the annulus or the annular space of this metallic hemisphere. So we have placed 3 thermocouple at 3 different locations along the length of this hemisphere. Okay, and we will allow the hot water to flow inside this annular space till we get the steady state temperature. Okay, and after this, a black body we have taken, a copper disc is there, and and on the copper disc we have applied thick layer of lamp black color in order to convert this copper disc to act as a black body, and which this we will connect at the bottom of this metallic sphere. So entire box will be closed, and heat transfer takes place from the surface of this black body or the copper disc to the surface of this hemisphere. So it is a closed box. No air is there inside the box. So no medium is there inside the box. So heat transfer takes place by the radiation. Okay, so in this way we can make the analysis. Okay. Now let's understand. We know for understanding for understanding this radiation, we know what is the radiation.
Okay, so for the radiation, no medium is required. Vacuum is the most preferable condition for the radiation mode of heat transfer, and radiation heat transfer takes place in okay, the radiation heat transfer propagates in the form of electromagnetic waves. No medium is required, and vacuum is the most preferable condition. There are different laws for the radiation, like Planck's law of distribution, Wien's displacement law, Kirchhoff's law, Lambert's cosine law, Stephen Boltzmann law, and so on. But if we talk about the classical law for the radiation, so the Stephen Boltzmann law is always the standard or the classical law for the radiation. Okay, so R is equal to epsilon sigma T to the power 4, where R is the where R is the amount of heat radiated. Okay, that is equal to epsilon sigma T to the power 4, where epsilon is the emissivity. Sigma is the Stephen Boltzmann constant, and T is the temperature on the surface of the body, that is in Kelvin. So epsilon is the emissivity. Okay. So what is emissivity? Emissivity is nothing but the ratio of the emissive power from the surface of any body to the emissive power from the surface of ideal or black body, or amount of heat radiated from the surface of any body divided by amount of heat radiated from the surface of ideal or black body. It is known as emissivity. So emissivity value is always equal to 1 for the black body, and the emissivity value lies in the range 0 to 1 for the gray body. And gray body is nothing but a real body or actual body, or the body on which we are performing the test. Okay. The sigma is the Stephen Boltzmann constant, and the standard value of the Stephen Boltzmann constant is this. That is 5.67 to 10 to the power minus 8 watt per meter square, Kelvin to the power 4. And T is the temperature in Kelvin. Okay, so this in this way we can calculate it. So for the radiation, we should know the different types of bodies. Different bodies are the black body, white body, opaque body, gray body, and so on. So what is black body? Black body is one which absorbs all the radiations incident on it. So for a black body, the absorptivity will be equal to 1, and the emissivity will also be equal to 1. Okay. So now let's go ahead. So here you can see what is this. Now we have taken a black body, right? So black, because we have taken a copper disc, and on the copper disc we have applied thick layer of lamp black color in order to convert the disc into act as a black body. So for a black body, the emissivity value is equal to 1. Okay, so epsilon value will be equal to 1. Now our expression reduces to this. That is, R, the amount of heat radiated, is equal to sigma T to the power 4. Right. Now let's see the arrangement. What we have done, we have taken a box, and inside a box this hemisphere arrangement is there, and this is the annular space of this hemisphere. Okay, we have taken the water, and we will heat the water with the help of this heater, or we will feed the water in the geyser, and the geyser will heat the water, and we will supply this hot water to flow inside the annular space, or the annulus of this hemisphere. Okay, we have placed three thermocouple T1, T2, T3 at the three different location on the surface of this hemisphere. So we will allow the hot water to flow inside the annular space of this hemisphere till we achieve the steady state. Okay, the steady state means temperature will be same at all the location. Now in this situation, what is this T4? T4 is the black copper disc on which we have applied thick layer of lamp black color. Now to act as a to act this copper disc as a black body. Now in this situation, this T4 we have not fitted this T4. We have not fitted the disc on this box, so it is open. Okay, so the temperature of the temperature of the surrounding will be equal to the temperature of this black body in this location. So after achieving the steady state, we will fit the disk. So after fitting the disk, now the entire box is closed. Now there is no medium inside this box. Okay. No air is there inside the box. That means there is no medium inside the box. Okay. So heat transfer takes place from the surface of this black body to the surface of this hemisphere. Okay, since no medium is there, so heat transfer takes place by the radiation from the surface of the black body to the surface of this hemisphere. Okay, so in this way, this setup works. Okay, and now we will derive the mathematical expression for calculating the Stephen Boltzmann constant experimentally. So let's see this. Now you just see, we know now the heat transfer takes place from the okay, from the hemisphere, from the from the surface of this hemisphere to the copper disk. Okay, heat transfer takes place. Heat transfer takes place from the surface of this hemisphere to the black body. Okay, so this amount of heat radiated we can calculate by applying the Stephen Boltzmann law. So according to Stephen Boltzmann law, okay, delta Q is equal to sigma 8 T to the power 4. Okay, so we can say, okay, so sigma 8 T1 to the power 4 minus T2 to the power 4. T1 is our the temperature on the surface of this hemisphere. Okay, and okay, so what is this TH? TH is the average steady state temperature on the surface of this hemisphere. What is it? TD? TD is the steady state temperature on the black body. Okay, so we'll apply the Stephen Boltzmann law and we can write this expression. Okay, delta Q is equal to sigma 8 TH to the power 4 minus TA to the power 4. Okay, now how can we calculate the amount of heat extracted? So amount of heat extracted can be calculated by the expression mCp delta T. But since the temperature change takes place with respect to time, so it is the unsteady state heat transfer. The temperature change takes place with respect to time. So we need to calculate dt by d capital T divided by d small t. That is rate of change of temperature with respect to time. Capital T is the temperature and small t is the time. Okay, so the expression becomes mCp d capital T divided by d small t. Okay, so that is nothing but the dt by d capital T by d small t is nothing but a slope of this temperature time graph. Now since this is delta q and this is also delta q, so we will equate our equation 4 with equation 3. We'll get sigma 8 th to the power 4 minus t to the power 4 is equal to mCp d capital T divided by d small t. Okay, so our interest is to calculate sigma. Okay, so okay, so we will keep this term a into t to the power 4 minus t to the power 4 in the denominator of this right hand side. So ultimately we'll get the sigma is equal to mCp divided by a times t to the power 4 minus t to the power 4 into d capital T by d small t. Okay, so this is how we have calculated okay, this is how we have derived the mathematical expression for calculating the Stephen Boltzmann constant experimentally. Okay, now let's see the application. So this determines the temperature of the sun from its energy flux density. Temperature of the stars from temperature of the stars other than sun, and also their radius related to the sun can be approximated by the by similar means. Okay, and we can find that earth temperature by equating the energy received from the sun and the energy transmitted by the earth under black body approximation. So and there are different many more applications for this procedure. Now you just see, remove the first of all in the setup, you just see here setup is there, so T4 is the disk. So first of all we have to remove the disk. Okay, we have to remove the disk at the top at the bottom from the bottom of the hemisphere. Okay, now we'll switch on the heater, will provide the power supply to the apparatus, will on the heater. Okay, and the heater will heat the water, so we will allow the hot water to flow through the annulus or the annular space of this hemisphere. Okay, so it will allow the temperature to reach the steady state. After achieving steady state, we will note down the temperature. We will note down the temperature at a different location on the hemisphere.
Now after this, we'll fit the disk at the bottom of the hemisphere. Now we'll note down the rise in temperature with respect to time till we achieve the steady state. Okay, so we'll note down the temperature rise due to the rise. Okay, we'll note down the temperature rise with respect to time till we achieve steady state. Okay, so in this way we can see the variation of the temperature with respect to times. Okay, so we will note down the values of we will note down the temperature value for the different values of time. Okay, we will tabulate those values, the value of the temperature for the different values of time. And after the, okay, so with the help of this tabulated value, we will draw a graph for the temperature with respect to time. So we will get a straight line like this. Okay, so we have to calculate dt by d tau. Why we are calculating this d by d tau? Because it is required to calculate the experimental value of Stephen Boltzmann constant, as in the mathematical expression this d capital T by d small t is there. Okay. So we can find the slope of this temperature time graph. Now after this, we will fit the disk or the black body at the bottom of this hemisphere. Now the hemisphere is entirely closed. Now the heat transfer takes place from the from the surface of this hemisphere to the black body. Okay, and it is a completely closed box, so there is no medium inside this. Okay, there is no air inside it, there is no medium inside this, so heat transfer takes place by the radiation from the surface of this hemisphere to the surface of this black body. Okay, we have to note down the temperature value at the different value of time till the steady state is reached. And after, okay, so we'll tabulate the values of temperature at the different values of time, and with this tabulated values we will draw a graph for the temperature with respect to time. Okay, now we will draw a graph for the temperature with respect to time, and then we will find the slope, the rate of change of temperature with respect to time. Okay, so it is nothing but a graph, it is nothing but a slope for this graph between the temperature and the time. Now you just see this this all about setup. I will tell you how to do this, and then we will we will select some values for those input parameter. We will make the simulation for the experiment for the same input values. Okay, so okay, for the, okay, just okay, so yeah, this is a setup. Okay, so we will give the input values here, and then we'll note down the temperature value on the hemisphere T1 T2 T3. Okay, the steady state temperature values, and then we'll fit the disk. After attaching the disk, you can see, you can observe the change in temperature. So that change in temperature we have to record at the regular interval. We'll get the different temperature values for the different time values. So my suggestion is you note down the temperature value every after 20 seconds. Okay, and so you will get, definitely you will be able to record around uh, 10 to 15 temperature values for every 20 seconds. So you can you tabulate, record these values, you tabulate the result for the temperature with respect to time, and with the help of this tabulated result, we can easily draw a graph for the temperature with respect to time. Okay. So you will get a straight line like this, and we'll find the rate of change of temperature with respect to time. So we can find the slope, and it is required for calculating the experimental value of Stephen Boltzmann constant, because this rate of change of temperature with respect to time is there in the mathematical expression for calculating experimental value of Stephen Boltzmann constant. Okay, now we'll feed all the, now this is a table. We'll make the simulation for the 3 trials. We'll note down the steady state temperature value on the hemispherical surface, the average steady state temperature on the hemisphere, T4, the initial temperature of the disk, that is nothing but the atmospheric temperature. And now the steady state temperature of the disk or the black body, and in the time in second at which we have achieved the steady state temperature for the disk. Okay, so how much time is required for achieving the steady state? So that time in second we have to record here, and the steady state temperature of this disk in Kelvin we have to record here. So okay, so we will there are three trials, so we'll make the simulation for all the three trials. Okay, so we'll make the three simulations, and for each and every trial we will note down the Stefan Boltzmann constant. So for trial number one, we will calculate Stefan Boltzmann constant. For trial two, we will again calculate Stefan Boltzmann constant. For trial three, we will again calculate Stefan Boltzmann constant. And then we will take the average value, and that will be the average simulated value of Stefan Boltzmann constant. And this average value of simulated value of Stefan Boltzmann constant will compare with the standard value of Stefan Boltzmann constant, that is 5.67 10 power minus 8 watt per meter square Kelvin to the power 4. Okay, the calculation is this. You just see here the mass of the copper disk. We can mention here. This is the formula. Okay, the mass of the copper disk, the specific heat of the copper disk. So you have to take proper specific heat of the copper. Radius of the disk. Okay, what is the size of this disk? After getting the radius, we can easily find the area of the disk by the pi r square. Okay, in meter square. Now the slope of the graph is d capital T by d small t. That is rate of change of temperature with respect to time. Okay, this slope we can calculate in Kelvin per second. Okay, now we'll substitute all these values in this mathematical expression. In this way, we can calculate this experimental value of Stefan Boltzmann constant in watt per meter square Kelvin to the power 4. And here you write the average simulated value of Stefan Boltzmann constant as a result. Okay. Now let's see okay, so you just solve these MCQs for your understanding. Simulated assignment question you can solve for your understanding, however it is not the part of the submission. Now let's click on the simulator. Okay, just please pay attention. Let's see how to perform this experiment. Okay, so just see this. First of all, what we'll do, now we have not fitted the disk. First of all, you click on the cross-sectional views. You enable this, so the internal structure can be visualized. You just see, I've enabled it. Now we can visualize the internal structure. Okay, so what about the setup? First of all, you just see this. We have filled, this is the valve. We will open it and we'll allow the water to okay to flow. We will allow the water to enter inside this geyser, and we'll on the geyser. We will provide the power supply to the apparatus. We'll on the heater, that we will on the geyser, and geyser will supply the hot water. Okay, so from this the hot water will be supplied uh, to this setup. So what about this setup? We have taken a box, and inside this box we have taken a hemispherical surface. This is the annular space of this hemispherical surface, or the annulus of this hemispherical surface will allow the hot water to flow inside the annular space of this hemispherical surface. So we have placed three thermocouple at three different location on the hemisphere, that is T1, T2, and T3. T4 is what? T4 is the temperature of this the temperature of this copper disk, or the temperature of this black body. And initially it is okay, we have not fitted the disk. Okay, so we'll allow the hot water to pass through the annular space of this hemisphere. Okay, and we'll keep watch on it and till we achieve. Okay, so we observe the temperature at the different location on the hemisphere. We keep watch on it till we achieve the steady state temperature. Okay, now this is the on off switch. Okay, on off switch for the setup. What is this? This is a temperature indicator. Here that temperature value will be displayed, and what is this? This is stopwatch. So the temperature value you can see here from the, so okay, so after fitting the disk, what will happen? Basically the box is closed. Now heat transfer takes place from the surface of this hemisphere to the black body. Okay, and there is no medium inside this box, so heat transfer takes place by the radiation. Okay, so you just see this when we fit the disk, so automatically the time, okay, so it will automatically it will on this power supply, and the temperature change takes place with respect to the time. So temperature change we can observe with the help of this temperature indicator, and time change we can observe with the help of this stopwatch. So my suggestion is that, okay, so it will okay, the process will take place very fast. Okay, so my suggestion is, you as per your convenience, you just note down the temperature value for every 20 seconds. Okay, okay, we'll note down the temperature value for every 20 second, and you have to note down these temperature values for every 20 second till we achieve the steady state. Okay, so tabulate those temperature value for the different time for the different time value. Okay, and to tabulate this, and with this tabulated values, we will draw a graph for the temperature versus time. So we get a straight line, and then we will find the slope of this graph, that is rate of change of temperature with respect to time. So how can I find this? We'll take the 2 points on this straight line. Okay, and then we can find the slope, or we can directly take the horizontal and the vertical projections. So we can directly get the change in temperature and the change in time value. So we can calculate the rate of change of temperature with respect to change in time. This can be calculated. Okay, you just see here the straight line. Okay, so we have taken 2 points A and C on this straight line. Okay, so we have suppose coordinate for A is x1 y1, coordinate for C is x2 y2. So y2 minus y1 divided by x2 minus x1, this will be the slope. Okay, that means, or simply you can say, take the projection, vertical projection, take the horizontal projections. Okay, so it's for the with the help of horizontal projection, we'll get the change in temperature value, that is dt value. With the help of this vertical projection, we'll get the change in time value, that is d small t value. Take the ratio, that is d capital T by d small t, that is rate of change of temperature with respect to time. We can find the slope. Okay, let's come to the simulator. Fine, so click on the cross sectional view. Fine, so after fitting the disk, it will automatically on heater. So we have to record the temperature. The temperature value will change, that will be recorded with the help of temperature indicator, and time value will also change, that will be recorded with the help of this stopwatch. So we have to record the temperature value for every 20 seconds till we achieve a steady state. Clear? So now let's make the simulation. Okay, so okay, so with the, by sliding the slider, we can change we can give the different heat input, we can give the different input values. When I will slide the slider on the left hand side, I can decrease the value. Okay, when okay, when I slide the slider on the left hand side, I can decrease the input values, and when I click when I slide the slider on the right hand side, so I can increase the values. Okay, like this. Okay, with sliding the slider, I can give the different input values to the mass of the disk and the radius of the disk, and so on. Okay, so let's make the simulation. Okay, so let's make the simulation. So first of all, give the water temperature. Suppose I have given the water temperature as 70 degrees Celsius. Okay, now the surrounding temperature. Okay, surrounding temperature is there. So I suppose I have given the surrounding temperature as near as room temperature, that is 30 degrees Celsius. Okay, now suppose I have given the mass of the disk as, suppose 6.2 grams, suppose. Okay, and suppose the radius I have given as 2.5 centimeter. Okay, now this cross sectional view is already enabled, so we can visualize the internal structure. Now we'll click on the power on. Okay, Okay, now we have clicked on the power on. Okay, now we have achieved the steady state. Just see this. T1 is 70 degrees Celsius. Okay, you just enable this T2. T2 is also 70 and T3 is also 73 degrees Celsius. What about T4? T4 is the temperature of the black body. So here we have not fitted the disk. So temperature of the black body will be equal to the surrounding temperature. So that will be equal to 30 degrees. If the surrounding temperature 30 degrees Celsius, so T4 will also be 30 degrees Celsius. That means when we have not fitted the disk, so the T4, that is the temperature of the black body, will be equal to the surrounding temperature. Let's see this. Let's check this. Whatever I am saying, you just see T4 is 30 degrees Celsius. Okay, that is equal to the surrounding temperature. That's it. Now what we have to do? Now we have to click on fit the disk. So as soon as I click on the fit the disk. So the okay, so it will on the power supply and automatically the temperature change will takes place. Temperature change takes place with respect to the time. So temperature change we can record with the help of this temperature indicator, and the time change we can record with the help of stopwatch, and we have to record the temperature value for every 20 seconds and tabulate the temperature value for a different time value. And those tabulated, for with the help of those tabulated results or tabulated values, we will draw a graph for the temperature with respect to time. After drawing the graph, we will calculate the rate of change of temperature with respect to time. Okay, so this process takes place very fast. So okay, so we have to record these values properly. Let's see this. So I clicked on fit the disk. Now you just see the temperature variation takes place, and at the same time also takes place. So every after 20 seconds you note down the temperature values. Okay, now we have achieved the temperature change stops. Okay, so we have achieved we have achieved the steady state. Okay, so the time at which I got this temperature value and a constant value of temperature, so that time I have to note down. Okay, in fact I have to note down the temperature change for every 20 seconds. Okay, and I have to note down the temperature at which we have achieved the steady state for the black body. Okay, now let's see this. So this, now you just see. So now T4 is this, the steady state temperature of this black body. Clear? So now the one simulation is over. Okay, the first trial is over. Now if I have to make the second trial, so okay, so yes, before this you just one trial is over. So you just take the screenshot, copy that screenshot, and paste it here at the required place in our Word file template. Okay, so I've already told you how to take the screenshot. You open the screen in the full screen, and you adjust the screen in such a way that all the details should be clearly visible. So here you can see I've adjusted my screen in such a way that I can see the setup, the complete setup. I can see all the input values on the right hand side. Okay, this cross-sectional view is already enabled, and on the bottom right corner I can see the results. In this situation, I will take the screenshot and copy that screenshot and paste it at the required place in our Word file template. Okay, now let's make the second simulation. So I will click on reset. Clear? Now okay, so let's see for this. Suppose this time I am making water temperature as suppose 79 degrees Celsius. Surrounding temperature is suppose 43 degrees Celsius. The mass of the disk is 6.7 gram. Okay, rate of the disk is, okay, radius of the disk is, suppose I have given the radius as suppose 3.7 centimeter. Okay, so you click on cross sectional view, so we can see the cross sectional view of this. Now click on power on. Okay, we have achieved the steady state. Yes, see, T1 is the tan equal to 79 degrees Celsius, that is the temperature, water temperature. T2 is also 79. T3 is also 79, that is equal to the temperature of the water. Okay, now we will click on fit the disk. So temperature change takes place. So we have to record the temperature change for every 20 second till we achieve the steady state. और okay, और वो टाइम भी नोट डाउन करना है जिस पर हमें स्टडी स्टेट मिला. So let's see this. I've clicked on fit the disk. See the simulation. Okay, now we have achieved. है ना, यही है फिक्स. वो टाइम वहां से नोट कर लो. क्लियर? इस तरीके से कर सकते हैं. रीसेट. चलिए थर्ड के लिए करेंगे. सपोज मैंने अभी वाटर टेम्परेचर ले लिया, सपोज 65. सराउंडिंग टेम्परेचर सपोज मैंने ले लिया 36 डिग्री सेल्सियस. मास मैंने ले लिया सपोज 6.9 ग्राम. रेडियस ऑफ डिस्क ले लिया सपोज 2.1 सेंटीमीटर. क्लिक on cross sectional view. I will click on power on. So you can see I've achieved a steady state. T1 is 65, T2 65, T3 65. Now I will select this T4. So this is T4. Temperature of the black body is equal to surrounding temperature. Okay, I will click on fit the disk. You just see change in temperature is there. Okay, record the temperature value, record different value of time. Now the temperature stop change time is 5 minutes 15 seconds. Okay, so 5 minutes 15 seconds. Okay, so just see this. Likewise, you have to note down the time for which we have achieved the steady state, right? So 61.81. That's it. And in this stage, you take the screenshot and copy the screenshot and paste it at the required place in our Word file templates. Okay, so in this way, we have done the 3 trials. Okay, and now we have to do like this. Okay, so here the table is there. So you just put the value for the first trial. What was the value? I taken 70 degrees Celsius as okay. So since it is the experiment based on the uh, okay, so based on the Kelvin. Okay, just give me a minute. Yes, just give me a minute.
Okay, so let's continue. So just see 1 minute.
Okay, so 70 degree Celsius was the temperature. So always remember for the radiation, we take the temperature value in the Kelvin. So 70 plus 273, that is 343 Kelvin. 343 Kelvin. Okay. Now T2 is what? T2 भी हमारा वही आया था. T2 was also ना, ये तो second case है. First case के लिए I am talking about. Okay, so first was again 70 है ना. First के लिए हमने तो it is also 343. 343 first case के लिए. T3 it was also 70 degrees Celsius, that is 343 Kelvin. So average is 343, right? Now the temperature of the disk. Okay, so the temperature of the disk was okay, I had given the 30 degrees Celsius as the surrounding temperature, so the disk temperature will be that too much. 30, that is 273 plus 30, that is 303. ओके, टाइम इन सेकंड, जिसमें मुझे वो टाइम नोट डाउन करो जिसमें स्टडी स्टेट मिला, वो आप नोट डाउन कर लो यहाँ पे. ठीक है, एक बार फिर से कर लेते हैं हम. ये मैंने परफॉर्म किया था, इससे मालूम पड़ेगा. रिसेट. देखो 70, यहाँ पर 30. तो मास ऑफ डिस्क कितना था? 6.2 grams. Radius is 2.5. Enabled cross sectional view. Power on. अभी देखो 70. तो टी स्टडी स्टेट मिल गया. T1 is 70, T2 is 70, T3 is 70. तो आई पुट, है ना, मैंने पुट किया 343 केल्विन, राइट, ये हो गया अपना 343 केल्विन हो गया। अभी मेरा ये क्या है, यहाँ पर मेरा ये 30 डिग्री सेल्सियस सराउंडिंग टेम्परेचर, तो T4 जो है डेट इज ऑल्सो 30 डिग्री सेल्सियस। ओके, सो आई विल नोट डाउन 30, दैट इज 303 केल्विन। ठीक है, तो ये तो पहले एवरेज टेम्परेचर कैलकुलेट हो गया, एवरेज स्टडी स्टेट टेम्परेचर ऑन द सरफेस ऑफ दिस हेमिस्फीयर। नाउ 303 इज द टेम्परेचर ऑफ द डिस्क। अब टाइम और स्टडी स्टेट टेम्परेचर देखेंगे हम। ओके, नाउ विल क्लिक ऑन फिट द डिस्क, फिट द डिस्क। देखो अभी टेम्परेचर चेंज हो रहा है और टाइम भी चेंज हो रहा है। तो ओके, स्टडी स्टेट टेम्परेचर 66.7 आ गया, 3 मिनट 39 सेकंड्स। ओके, 3 मिनट 39 सेकंड्स, सो फाइन। ना द टेम्परेचर 66.77, 3 मिनट 39 सेकंड। तो यहाँ पर हम क्या नोट डाउन करेंगे, टाइम इन सेकंड, 3 मिनट्स 39 सेकंड, सो 3 into 60 plus 39, so that is 219 seconds, 219 seconds, and the temperature is, steady state temperature क्या आ गया आपका, it is 66.77, so केल्विन में कन्वर्ट कीजिए, 66.77 plus 273, so 339.77, so 339.77। ठीक है, अभी चलो सेकंड केस के लिए करते हैं, रीसेट, क्रॉस सेक्शनल व्यू इनेबल्ड। इस बार मैंने सपोज I'm performing this for 60 degrees Celsius, surrounding temperature 38 degrees Celsius, mass of disk is 5.9 gram, and radius is suppose 2.2 centimeter. Okay, power on. So you just see, I mean, steady state आ गया 60 60 60. Okay, so you just see 60 plus 273. So this is 333. Okay, 333. तो 333 यहाँ पर आएगा 333, ये भी 333, और T3 is also 333. It has achieved steady state, so average steady state temperature on surface of hemisphere is 333. अब temperature of disk ये कितना है, it is equal to surrounding temperature 38. So 38 plus 273 केल्विन में कन्वर्ट किया तो 311, 311 कर लिया हमने यहाँ पर। अभी हम फिट द डिस्क पर क्लिक करेंगे, record the temperature value for every 20 seconds for drawing the graph for the temperature with respect to time. ठीक है, so fit the disk. Now you just see the temperature is changing with respect to time. Record the temperature for every 20 seconds for drawing graph for temperature with respect to time. Now the temperature stop changing 56.98 times. Okay, so the time was 4 minute 49 second. Okay, and 59.98 temperature, 4 minute 49 second. Okay, so 4 minute 49 second is 4 into 60, okay, plus 49, that is 289 seconds, 289 seconds. Okay, and the steady state temperature on the disk is कितना है, it is 56.98. so convert this in Kelvin. (56.98) plus 273, so 329.98, 329.98. Okay, that's it. And in the similar fashion we can make the analysis for third trial also. Okay, if we'll try some different value, you just click on reset. This time suppose I have taken 73 degrees Celsius, here I have taken that at my surrounding temperature as 54 degrees Celsius. Mass of the disk as suppose 5.6 gram, radius as 1.5 centimeter, cross sectional view, power on. तो अभी देखो 73 डिग्री सेल्सियस स्टडी स्टेट आ गया, T1 T2 T3 73। ओके, सो 73 केल्विन में कन्वर्ट करो, 273 प्लस 73 346 346, it is also 346, it is also 346. So average steady state temperature on surface of hemisphere is 346. Temperature on the disk, temperature on disk कितना है? That is T4 equal to surrounding temperature 54 डिग्री सेल्सियस। इसको भी केल्विन में कन्वर्ट करके लिखो, 54 प्लस 273, 54 प्लस 273 327, 327। ठीक है, नाउ भी टाइम और स्टडी स्टेट टेम्परेचर का देखेंगे। ओके, नाउ क्लिक ऑन फिट द डिस्क। नाउ यू कैन सी द चेंज इन टेम्परेचर विद रिस्पेक्ट टू टाइम। Okay, temperature of changes, the time was 4 minute 2 seconds. Okay, 4 minute 2 seconds. Okay, 4 minute 2 second, that is 4 into 60 plus 2, that is 242 seconds. Now let's see the time. Sorry, temperature. Time we have already noted down. So let's see the temperature, 69.53 degrees Celsius. Okay, 69.53. Convert in Kelvin. So 69.53 plus 273. So it is 342.53. 42.53. Okay, now the table is complete. Okay, so we have done so we have done 3 trials. So for trial number 1, okay, we have the TH value, and that is average steady state temperature on the surface of hemisphere, and this is the total time, and this is the average, and this is the steady state temperature on the copper disk or the black body, that is TD, and this is TH, and that is the time. Okay, and we have recorded the temperature value for every 20 seconds. So now we can draw the graph for the temperature with respect to time. So we can find dt by d capital T by d small t, that is rate of change of temperature with respect to time. So we'll feed all these values in the mathematical expression. Okay, so we can calculate Stephen Boltzmann constant for the trial 1 in the similar fashion. In the similar fashion, we can calculate the Stephen Boltzmann constant for the trial 2 and trial 3. And finally, we will calculate the average value of Stephen Boltzmann constant, and that will be the average simulated value of Stephen Boltzmann constant, and that value should be almost same as the standard value of Stephen Boltzmann constant, that is 5.67 into 10 power minus 8 watt per meter square Kelvin to the power 4. Okay, so for what was the formula? Formula we have already seen the procedure. This is the formula. Mass of the copper disk is specific heat of the copper. We have to put here rate of change of temperature with respect to time. The slope we can find with the help of the graph of temperature with respect to time. Area we can calculate by pi r square. R is the radius of the disk. TH is the average steady state temperature on the surface of hemisphere, and TD is the steady state temperature on the copper disk, that is steady state temperature on the black body. You will feed all the value, so we can calculate this we can calculate the experimental or the simulated value of Stephen Boltzmann constant. So we have to calculate this simulated experimental Stephen Boltzmann constant for all the 3 trials, and then we'll calculate the average value, and okay, we'll calculate the average value. Okay, so that will be the average simulated value of the Stephen Boltzmann constant. Average simulated value of the Stephen Boltzmann constant, and this value will put here, and we will compare the average simulated value of Stephen Boltzmann constant with the standard value of Stephen Boltzmann constant, that is 5.67 10 power minus 8 watt per meter square Kelvin to the power 4. So this value, the simulated value should be almost same as the standard value. That's it. In this way, we can complete the write-up of this experiment, and at the last, you have to give the feedback. And after giving the after submitting the feedback, you have to take the screenshot of this feedback and copy that screenshot and paste it here in the Word file template at the last below this conclusion part. Okay, in this way you can create the soft copy. You can complete the write-up of this experiment in the soft copy. In the Word file, you convert this into a PDF file, and you upload this PDF file on the LMS. I will create the activity on the LMS for submitting this virtual lab experiment, both the virtual lab experiment and soft copy, and then you take the printout of this write-up and you submit this write-up in hard copy for assessment. That's it. In this way, you can complete the write-up. Fine.
Okay, sir. Yes, sir.
Understood? Yes.
Yes, sir.
समझ में आ गया ना अच्छे से?
हाँ हाँ सर.
Okay. So no doubts ना?
No, sir.
Okay. So okay. So can we wind up the class?
Yes, sir. Sure.
Okay. Fine. Okay. So just a minute.